This will probably be the last video I'd make before going back to Indiana. So I'm still at my parents' house. It's been a little hard with the internet, but soon I'll be connected all the time again. But anyway, we're into chapter 1.3. We already talked earlier, 1.1, about the axioms of probability, and so I'm just going to restate those in 1.3 and then do a few just small proofs of how you would use the axioms to prove some fundamental principles in probability. The axioms were stated in 1933 by Kolmogorov. Um, Axioms, they're like self-evident truths. They're the basis for probability theory. You can't prove them. They're just stated facts that have to be true in order to be able to do probability and build from it everything we need. So again, imagine S is a sample space, A is any event of that sample space. The function P is a set that goes from events to the sample space 0, 1. And it's a probability function. So P is a probability function such that the probability of any event A is bigger than or equal to 0. So again, I don't prove this is a stated fact. It kind of makes sense. The probability of any event is bigger than or equal to 0. The probability of the sample space is 1. In other words, when you run an experiment, it's a sure thing that the sample space will occur. If A1, A2, A3, up to forever and onwards, if these events are mutually exclusive, in other words, they don't intersect, if you take any sets I and J, they don't intersect each other, the probability of their union is equal to the sum of their probabilities. So again, just imagine that you had this big space, right? Here's A1, A2, A3, A4, A5, A6. And if I wanted to find the probability of their union, I would just add the probability of him and him and him and him and him and him. So it's a nice property. When things are mutually exclusive, you can add away and you don't have to worry about their intersection because it's empty. So with those axioms, we can go through and prove a lot of theorems in probability. So again, oh, by the way, if P satisfies those axioms, we say the number P of A is a probability, the probability of event A. So the first theorem we're going to prove is probability of the empty set is 0. And again, I think most people just, oh, of course that's true. But now that we have axioms, we can prove everything else that we need in probability from those axioms. So again, this might seem a little bit silly how I'm going to do this. I'm going to let event A sub 1 be the sample space S, and A sub I for every other possible event going to infinity be empty set. So really I'm defining A sub 1 as S and every other event is empty set. And then we know A sub 1 through A sub infinity are mutually exclusive events. Because the intersection of empty set with empty set is empty set, and S intersects with empty set is empty set. So now I'm going to use axiom 3, which says the probability, well, S is just the union of all these events. And by axiom 3, it said the probability of the union of these events is equal to the sum of their probabilities. But we can just break that up. That's the probability of A sub 1 plus the probability of A sub 2, 3, 4, all the way up to infinity. And so we know that probability S has to equal probability of S. So this thing has to be 0 then. So what I'm saying is this thing adds up to be 0, but we know probabilities can't be negative from another axiom. So the only conclusion we can make then is probability empty set has to be 0. And again, I use the other axiom. I think it is axiom 1 that says probability of event is greater than or equal to 0. So yeah, I mean, if you add a bunch of things that get 0 and these can't be negatives, then empty set has to be 0. So it seems kind of silly to do a proof like that, but we have just proved the probability of empty set is 0. Down below in theorem 1.2, I mean, maybe I'll just state it instead of showing it, but all we're doing here now is saying the probability of the union of a finite number of events is equal to the sum of the probability of those events. And the only difference between this and the axiom is now we're saying this holds for a finite n. And so all I'm going to do a similar trick down here where everything after, all the sets after n, I'm going to just define those as empty set. And you can kind of see here I'm doing that same trick. I'm going to break it up into the sum of the events that aren't empty set and then everything that is empty set. And so you can kind of see where I'm going with that. So this is just nice. It lets us do it on a finite scale. If A and B are mutually exclusive, then probability of A or B is just the sum of A and B. So let's do, there's another, that we use this fact all the time. Let me see. Oh, yeah, probability of A is less than or equal to 1. We said probability of S. What did we say in the axiom? Probability S is 1, right? So now what I'm showing here is probability of any event A is less than or equal to 1. Why? By theorem 1.2, we're allowed to do this. This is two finite events, and we're allowed to break it up into the sum of their probabilities. We know A and A complement make up the entire sample space, so together their probability is 1. And I know probability of A complement has to be bigger than or equal to 0. So that means this can't be more than 1, at most 1. I mean, if this is 0, this would be exactly 1. And if this is, takes on any value greater than 0, then this has to take on a value less than 1. So this is a nice fact. I mean, a lot of times if I want the probability of A, we know that's 1 minus the probability of A complement then. So if you can't find A, sometimes it's easier to find A complement and then subtract from 1. So I'll use that technique a lot, and so I feel like that's a really important statement there. This is just the classical definition of probability in a sense that all I'm saying is if you have n equally likely outcomes in your sample space, then the probability of each of them is 1 over n. So imagine you have a fair deck of cards, 52 cards in a deck, and you randomly choose a card out. What's the probability? You get a queen of hearts. So there's only one queen of hearts in the deck, so this is 1 over 52. The probability of a black ace or a red queen, those are two mutually exclusive events, so probability of a black ace plus the probability of a red queen. I'm allowed to add them because they're mutually exclusive. There's two black aces in a deck, and there's two red queens in a deck. So this is going to be 4 out of 52. Which is 1 out of 13. And your problems, I'm happy. If you leave it like that, I'm not caring if you reduce. Don't switch it to decimals. This is much easier to think of probabilities for me as fractions or ratios. Not a heart would be 1 minus the probability of a heart. And hearts, a fourth of your deck is hearts, so 1 minus a fourth. So this is 3/4. So I just used the idea of complement. Probability not a heart is 1 minus the probability you do have a heart. So this just says if you combine, right, if the event occurs NA times and everything's equal likely, it's just going to be NA over N. And I think my video is probably getting too long, so I might just leave these last two examples. I have them in the solutions. I think, yeah, maybe I should just say a little bit of example 2. This is just a nice one with algebra and assuming blood types are mutually exclusive. Up here, I'm going to select a number from 1 through 100. What's the probability it's divisible by 7? The only way a number can be divisible by 7 if it has the form to be divisible by 7, number has form 7k. You know what I mean? Because if k equals, well, k is equal to 1, 2, 3. In fact, the biggest k can be to still be less than 100. I want to say is 14, right? 14 times 7, I know this is kind of lame, is 98. Yeah, so k could be 1 through 14, right? Because 7, 14, 21, as long as it takes on the form 7 times k, and k goes from 1 to 14, it will be divisible by 7. So that means, what is the probability that is divisible by 7? It looks like 14 numbers out of 100 will be divisible by 7. Again, I'm happy if you leave that, or you can say 7 out of 50. So I'll leave 1-3 then. That is 1-3. It's a pretty fast section. And when I get back to Indiana, then I'll do section 1-4. So until then, enjoy. I'll be posting homework soon also.